this lot. Thankfully, that earthquake's serious. I'm just hoping there won't be any aftershocks. I spoke too soon. Better go and check the plane's all right. After I've answered the science line.
Stella, we've been... Are you all right?
Yeah, things got a little rocky here. What's the problem?
Well, Stella, we want to know what rocks are.
Yeah. This one's got crystals in it.
Yeah, look at this one. It's all gritty like sand. That's because there are lots of different rock types. I mean, look at these.
And what about this? It's mineral water, but I can't see any minerals.
No. So, Stella, what are minerals? And what are rocks actually made of?
I'm onto it. There are all types of different rocks, and they all look different from each other. But there's one thing all rocks have in common. They're made from minerals. Now, some are soft, like the walls of this cave. This is sandstone. Others, like granite, are extremely hard. Some rocks are granular, like millstone grit, whilst others are smooth, like obsidian. Now, these are made from minerals which occur naturally in the Earth's crust. There are over 200 minerals, but most rocks are made from different mixes of about 20. Minerals are the ingredients for rocks. In cooking, these ingredients could make cakes when mixed in different quantities and cooked in different ways. And it's the same with minerals and rocks. Minerals are the ingredients and rocks are the results after mixing minerals in different quantities and cooking them in different ways. But what are minerals themselves made out of? Well, some minerals are made out of elements: sulfur, gold, copper. Well, other minerals are made out of compounds, which are combinations of elements. Hematite, also known as iron ore, is a mixture of iron and oxygen. So different combinations of elements give different properties to minerals. I think it's time how we investigate it.
This is a quarry where they extract granite, a rock that's used for everything from curbstones to cathedrals. Why? Well, because it's incredibly hard. And hardness is what I'm interested in. That's why I've come to see a geologist called Anna Grayson. Anna, what are the minerals in granite?
There's 3 minerals in granite. There's quartz, there's mica, and there's feldspar. Now, this is fresh granite, this is clean granite, and you can see the minerals very clearly here. There's your mica, sparkling, you see it? And there's the quartz, this sort of white to grey clear mineral. And this pink is the feldspar, nice and hard there.
So that's mica, quartz and feldspar. Now, all minerals have a different hardness, and Anna's going to help me find out how hard each one is. These are 2 other minerals, calcite and gypsum. But which is which?
If I were to scratch one with the other, I could work out which was the harder. Should we try?
Yeah. A harder mineral will be able to scratch one that's not so hard. Anna knows that calcite is harder than gypsum. So as it's been scratched, this mineral must be the gypsum, which is softer than the one that scratched it, the calcite. It's called the scratch test. Can you use this to tell the difference between all kinds of different minerals?
Yeah, you certainly can. And there was this wonderful man about a century ago called Frederick Mohs who had 10 minerals of different hardness, and he arranged them in order to form what's called the Mohs scale of hardness. And based on that, I've got this. That's Scratchometer! 1 is the softest and 10 is the hardest. You see, everyday objects have hardness as well. A fingernail is round about 2, and a copper coin is round about 3.5. So if you were to get the calcite, you could work out its hardness. Have a go.
Right.
Try scratching it with your fingernail. Are you making any inroad there?
No, nothing.
Try it with a copper coin.
Try the coin. Oh, yes.
Made a very faint scratch, hasn't it?
So I now know the coin is harder, the fingernail is softer, so must be in the middle at 3.
That's right.
I guess my investigation is to find out which of these goes in which spot on the scratchometer.
Exactly right. And you've got 45 seconds starting from now.
Right, start with my fingernail. It scratches none of the granite minerals. How about talc? Yes. Softer than a fingernail. Now the coin. Feldspar, no. But this, softer than a coin. Mica. Penknife. That's steel. Steel has a hardness of 6, and it just scratches the feldspar. Now for the ruby.
10, 9,
It doesn't scratch the diamond,
8,
so the diamond's
7,
harder.
6,
But it does scratch
5,
the quartz.
4,
Quartz is not as
3,
hard as ruby, and
2,
diamond is the hardest of all.
1. OK, let's see how you did. Talc, mica, feldspar, quartz, ruby, diamond. Excellent, Howie.
So how do you get from minerals to this rock? Well, one way's happening over there. When a volcano erupts, it's the beginning of one part of something known as the rock cycle. Now, there are 3 types of rock in the Earth: igneous, sedimentary, and metamorphic. Volcanic rock is called igneous rock, and igneous comes from the Greek word meaning fire, and that's where it's coming from. Molten rock, hotter than fire. But how is it hot? The center of the Earth, the core, is thousands of degrees Celsius. It's hot enough to make molten rock, which is what the next layer, the mantle, is made of. The Earth's skin, or crust, is anything from 5 to 75 kilometers thick. It's cooler, and so it's solid. Sometimes the molten rock pours out through volcanoes. This is brown sugar in water. When heated, it becomes like toffee. But when I pour it on this tray, it cools and solidifies like molten rock. And this is what happens with igneous rocks. Igneous rocks have a crystal structure, and the size of the crystals depends on how quickly the rock cools. The quicker it cools, the smaller the crystals. Now, once the rock is outside, things begin to change, and this is due to the weather. Take this rock. It's very hard. I can't smash it with this hammer, but the weather can.
What? But how does the weather do it? I don't know, maybe the rain could wash it away. No way, it would be too slow. It would take forever.
Stella, are you sure it's the weather?
I'll show you. Rainwater gets in the cracks in a rock. And to show you what happens, I filled this iron flask with water, and I'm going to put it in ice. Rainwater gets into the cracks and freezes. The ice expands as it forms, and the force is large enough to split the rock. Eventually, the rock has so many cracks. This has been very well weathered. Easy. But what happens to the bits of rock that break off? I think Howie needs to investigate.
Ah, what a view. I love painting. But why am I painting rocks? I blame Mark Lee. He told me to do it.
Hi, Howie. How's it going?
Hi, Mark. Why am I painting rocks?
Well, you wanted to investigate what happens to rocks when they get weathered.
Well, they'll get washed away.
Yeah, but where do they go to? That's the big question. We'll place the pebbles on the beach now. We can see the tide come in, and we'll see where they've moved after the tide.
We lined up the painted stones between 2 posts. Next, we added some boulders, which we also marked.
OK, let's go.
Then, all we had to do was wait for the tide. All along the beach erosion, The sea wears big boulders, smaller and smaller. The boulders themselves are made of mud, sand and pebbles. The mud and sand are washed away by the sea, releasing stones. The tide waits for no one, and the sea soon set to work to move sand and stones. Whilst the tide was in, Mark showed me what was at the end of the road on top of the cliff. Whoa, that's pretty dramatic stuff. How fast is this cliff eroding?
Well, it can be up to about 20 metres in a single year. So the bit of road that we're standing on now, within a couple of months, could join the rest of it right down there at the bottom of the cliff.
So the cliff is where the rocks come from in the first place. 5 hours later, the tide had gone out.
Right, this is where we set the stones up.
And there's only 2 left, and even they've moved, what, half a metre? I wonder where the others are. Who's going to go and look for them? Mark, I've got one! It's travelled 50 metres! I guess that's because it's smaller.
Right, but the smaller stuff is the sand and the mud. And that gets moved too. Look, you can see it in the sea.
The sea is brown with mud and sand, clawed from the beach and cliffs, already on the next part of its journey.
Over the years, bits of sedimentary rock settle on the seabed because of gravity, and the layer gets to be very thick. And the thicker the layer gets, the more pressure is exerted on the bottom of it. As the particles get squashed, the water is squeezed out, leaving deposits that cause a process called cementation, where the particles are cemented together. Over time, the squashing and cementing of the sediment forms sedimentary rock. Rocks made of sand that have been compacted and cemented are called sandstone, like the walls of my cave. This means that this cave is in an old sea or lake bed. The water disappeared long ago, and the process takes millions of years. So this sandstone is 235 million years old. Washed in with the sand are shells and other organisms, and they get squashed as well to form limestone. And limestone is another sedimentary rock. This is limestone, but this is not the end of the story. After this sedimentary rock's made, the weight of the layers pushes them deep underground, where the earth can heat and squash the sedimentary rock further. Now, when it does this, the rock changes yet again, and this third type of rock is called metamorphic. The heat and pressure which makes metamorphic rocks can give them special properties, as Howie's investigating.
These were all made by Jan Rees, an artist who works in slate, which is a metamorphic rock. He'll help me to investigate its properties. Why is slate so good to work?
Look, I'm not going to tell you. I'd rather set you a little challenge, if you don't mind, to carve your initials as small as you can. Would you take on that challenge?
Sounds good.
Now then, Howie, here are 2 rocks, a slate, which is a metamorphic rock, and this is sandstone, a sedimentary rock. Now, when you work in these 2 materials, I'm sure you'll find why slate is so special.
It's not just a question of scratching. Each stroke has to be chiselled both ways to give it depth. 7 millimetres. Not bad. Oh. Sandstone's not so easy. Bits keep breaking off. making me work bigger. This time, the smallest I can manage is 19 millimetres. Compare that to the 7 millimetres with slate. So why is that? I guess because the particles are much smaller and more tightly packed together.
And of course, in the sandstone, the particles are much bigger.
Big particles have more air between them, making the sandstone weaker. That's why bigger bits break off. Slate's particles have been squashed smaller and tighter through the metamorphic process, which means finer carving. I could tell by feeling the dust that came from the rocks. This is the sandstone, and it's really gritty and
Much
quite
more
coarse.
gritty, that's right.
And the slate, oh wow, that's, well, it's like handling flour, isn't
Yeah,
it?
it's like velvet, isn't it?
Yeah, totally different. Well, thanks for your help, Jan. I'll be off.
Hey, hold on, boyo. I have another challenge for you that will show you another wonderful property of slate. I want you to make your initials as big as you can out of these two materials.
For big letters, there's no need for a chisel. Just a hammer. There. What do you think?
It's great.
Now for the slate.
Wait. There's somebody I'd like you to meet.
The slate is being split by John Tudor Jones into tiles 5 millimetres thick. He can do this because when slate is formed, it's squashed into very thin layers, making it good for things like roofing tiles. That one piece of slate produces 16 tiles, which means I can write my initials. This big.
Both sedimentary and metamorphic rocks can work their way to the surface and be eroded by the weather and make their own rock cycles. The other possibility is that metamorphic rock can get heated and melted down, ready to be thrown out of the earth again to make igneous rocks. So the whole thing starts again. That's why it's called a rock cycle. What's the connection here? How can limestone, which is a sedimentary rock made up of mostly shells, become marble, which is a metamorphic rock?
The limestone would be in the Earth's crust. Yeah, and if other sediment was laid on top, then it would be buried.
And if more and more stuff was deposited, then the limestone would get squashed down.
And as it gets pushed down, it gets closer to hot rock in the centre of the Earth.
Right, heat and pressure will cause the sedimentary rock to change.
Yeah, and under the right conditions, the limestone would change to marble.
Which is a metamorphic rock.